And section 5.3 is simply taking 5.1 and 5.2 and really looking at a little bit more math involved. In chapter 6, we're going to get into friction and coefficients of friction, and then we're going to get into air resistance. We're going to look at other specific or special types of forces, like even circular motion, right? With centripetal force we're going to talk about, but that's all chapter 6. So chapter 5 is like an intro to forces still. But 5.3 is really where we get into some of the problem-solving techniques. So I'm going to start with, this is problem on page 108. This is sample problem 503. So we're going to start with this one first. And what we're going to do from here is we're going to go through each of these one at a time. So let's take a quick look at what it is. Here's the problem itself. All right, there's the problem itself. I think a diagram is given, so I'm going to put the diagram next to it also. Obviously, if you have the electronic version of the book, you could be viewing this as well.
It's the same like thing as last time.
Sure.
With the
Is it happening again?
image.
Oh, man. I don't know.
Wait, which page was that on?
So this is page 108. Any better when I do that? Yeah, there we go. It gets a little bit better, right? Okay. So let's take a look at what we're going on here. So first, the figure on the right shows a block S sliding with a given mass. The block is attached, it's free to move along the horizontal frictionless surface. And that happens on the test a lot with multiple choice problems. A lot of the time, multiple choice problems will involve something that's frictionless because it's less work for you to do, and it's a multiple choice problem. If friction is involved, it'll probably be either they'll give you the force, so you don't have to worry about mu Fn, or it'll be a problem all about friction that you have to actually solve. But if you're given a lengthier problem like this, a multiple choice type problem, it would most likely be frictionless. Frictionless surface connected by a cord that wraps over a frictionless pulley to a second block H, called the hanging block, with a mass given of 2.1. The cord and pulley have negligible mass compared to the blocks, meaning they are massless. Later on, we'll talk about what if the cord and the pulley have mass, and that does affect the answer. But that's not until chapter 7 or 8. The hanging block H falls as the sliding block S accelerates to the right. First, let's talk about this problem. Let's write down something in big letters at the top. Big letters here. If there's tension in the rope, the system moves with the same acceleration for each block. If there's tension in the rope, the system moves with the same acceleration in each block. That's a really important point to make. It's as if they're moving together. Every inch that the block H falls creates 1 inch of motion horizontally for block block S. So what's going to happen for all of these problems is you're going to notice that as we go through them, you're going to assume that the acceleration of this one falling is the same as the acceleration of this one sliding. Now, one of them will be an AX, that's block S, and then block H will have AY, vertical acceleration. Okay, so keep that in mind as we go through these types of problems.
What would be like another example, like not like a pulley, like something else, but like
They weren't?
where there'd be tension and it would move with the same acceleration.
It's only if there's not tension that this will happen. So when there's what's called slack in the line, so imagine the cord is on the ground. The first one moves, then tension engages. So the entire beginning part, when it's moving by itself, the other one isn't moving. So whenever there's tension, you treat it as if they're like glued together. So if I had two masses glued together, they'd be moving with the exact same motion. That's happening here. Remember, what does a cord or rope do actually? It pulls on both ends. So one force feeling is the same as the tension in the other part of the line. Now, the other part to recognize is that the real key to a pulley or a rope is to redirect the force. Redirect. For example, when you see people turn around, take a quick look, you see them cleaning the windows, right? And you see sometimes the device that they're all standing on will go up and down, right? Well, there's a pneumatic device that's literally pulling on one of the lines, and by pulling down on this line, what does it do? It lifts up because there's a pulley at the top. So a pulley and a rope together are really just used to redirect the force. That's all that's happening here. So block H is clearly pulling down on the rope.
In that system, wouldn't the accelerations always be opposites, though, because always going to...
Well, they're different directions also, Matt. So altogether, we're going to say that this acceleration is in the negative y direction. This is in the positive x direction. So this will be positive when we do some of the forces in the x. This will be negative acceleration when we do some of the forces in the y for this block. But we're going to look at some of the forces in both directions for both blocks.
So like in terms of like Newton's first law, the force pulling down the block would be the gravity. Or like the force pulling down the gravity and the reaction to that would be the tension of the rope pulling up.
Correct. But we don't know if they're going to be balanced because, again, if one exceeds the other, then it's going to be accelerating down. And that's going to be the goal to this problem, I think. Yeah, find the acceleration of the block, the acceleration of the other block, and then find the tension in the core. Those are the classic three things you're going to look for: is tension and acceleration.
I was just thinking, like, so this is like a problem without friction, but I guess in real life where there is friction, like the mass that's hanging would have to overcome the frictional force.
What frictional force?
If there was frictional force, I'm saying, right?
If it were against the wall or if air resistance were there. Yes, both of those things. But the one that's sliding has kinetic friction between it and the floor if there were friction involved. And that would involve the x direction for the block S, and it would be in the y direction for block H. The frictional forces is what I'm saying. Yeah. So let's start this problem like we do all problems. What do we always start force problems with? Yeah, free body diagram. So let's take a look at block S first. Block S has tension acting to the right. I call it FT. You can call it capital T. That is fine with me. I have a tendency to call it FT, so I'm going to continue with that nomenclature. I'm then going to write the weight, or FG, and this I do write FG, and they're calling this FGS for block S, and that's fine. And then FN acting up. If there was another block on another surface, I would have called that FN1 or FNS, meaning the normal force on block S. But because the other block does not have a normal force, we don't have to worry about the actual other block or naming FN with 1 or 2. Then for block H, we've got the weight of block H pulling down, and we've got tension pulling up. So this diagram in this first problem in your book gives you the free body diagrams, literally. Right? We're just redrawing them with dots. So they're on the diagram, right? If you notice, they're all on the diagram already. Now, we know that we're going to call one of the masses M, capital, and the other lowercase. So let's actually specify those then. It's not very clear, actually. Let me do it this way. Hold on, so you can see it better. Okay? Capital M for mass of block S, lowercase m for block H. Now, once we've got the free body diagrams, these problems are not, you can't see it, but it doesn't matter at this point. These problems are not really difficult because there's only one equation. If that's not clear to you, if that hasn't sunk in yet, write that down also. You're only ever going to use F net equals MA. F net equals MA. It's always going to be the same equation. That's the nice part about Newton's laws and dynamics, whereas with kinematics, we had many choices to make. The problem could have changed each time. No, there's one formula here. One governing formula. And then from there, we're going to replace certain things. So let's go ahead and start writing those governing formulas. So for mass M, the sum of the forces in the y direction equals MA in the y direction. In the y direction, I've got Fn pulling up. I've got the weight of block S pulling down, and that equals MAY. That's the y direction for the first block. Does it say anything about this block coming off the surface? Do you think it's going to come off the surface based on the way tension is pulling? So what can we say? The way tension is pulling shows me that it's only pulling it to the right, correct? It's not like it's pulling it at an angle like when you lift on like a sled, Remember, if you attach a rope to a sled, the sled might come off the ground a little bit, right? Because you're pulling at an angle.
F nat y is 0.
Good. So this is 0 because AY has to be 0 for the first block. It's not accelerating up or down. It's in vertical equilibrium, vertical translational equilibrium in that case. So this becomes 0 in this problem here. Again, because AY is 0 for the first block. Is that going to be the same case here? No. This one is accelerating downward. I can tell you that already because this block is going to be pulling down. Or it's at rest. It's one of the two, but it's not accelerating upward. There's no way that block S is just magically moving to the left. Block S cannot move to the left because there's no force pulling it to the left. So this block either has to be at rest or accelerating downward. It's one of the two things, but it's not accelerating upward. But the first block, I know vertically, is in a state of equilibrium. So does that do anything for me? Fn and FGS, they're balanced. All it tells me is that I can move this over, right? That's all it really tells me.
It also tells you that it's moving to the right because there's only one force acting on it.
Good. We know it's moving to the right. How come? Because there's no what?
There's no like equilibrium horizontal.
What would it be normally?
Friction.
Yeah. There's no friction in this problem, right? So Spencer said, hey, you know what? Because tension is the only force acting to the right, there's going to be horizontal acceleration on this block for sure. Because there's nothing pushing back. So it's got an unbalanced force, then unbalanced forces create changes in velocity. Remember Newton's first law. Equilibrium means the velocity is either constant or the velocity is 0. The minute you have an unbalanced force, it creates a change in the velocity, aka an acceleration is what it creates.
If we go to diagrams, if the forces are equal, do you want us to like draw a line to say that they're congruent?
To say that there?
Congruent with vectors.
Meaning Fn and FGS you're talking about?
I can't remember if we did that last year.
I don't think I did. You mean like cross them off to show that they cancel?
Draw like a congruent line, like if you're doing geometry, show the lines are equal.
No, the free body diagrams on the exam, the length of your vector and stuff, they're not going to be, they're not going to be analyzing, is the length of this one the same as that length? No. But this formula, this will tell us that. Yeah. So this, all we gain from this formula is that Fn, all we gain from this formula is that Fn is equal to the weight of block S. And I gain that information simply by adding this over to the right-hand side. Well, just so we know, how do we designate weight? The weight of an object, what's the formula for that? mg. And the first block was capital M. So this is the formula, or this is the result we gain from some of the forces in the y direction. Remember, the block S has mass capital M, so it's capital M times little g, and that is the weight. Remember, people, that this g value is 9.81. It is not negative 9.81. If that's not clear to you, you need to recognize that. This little g here is 9.81, or 9.8, whatever. But it's not negative. The negative is already accounted for. Do you see it right here? That's where the negative plays a role already. We've already recognized that gravity is pulling it down. This g is the magnitude of acceleration, which is just 9.8. This is where the negative already came into play. Now, the x direction for mass capital M. Let's take a look at the x direction. I want to make sure I'm off the screen. Okay. So we have the sum of the forces in the x direction equals max. Oops. max. Max. That happens a lot, I'm sure. Calculus, right, by now? Okay. So what's acting in the x direction? Only tension. And it's acting to the right. So tension equals max. Now, that m, because it's the bigger mass, I should be using a capital M. Agreed? This is the bigger mass of the two. So when I'm doing these formulas, I should be consistent and use a capital M and a capital M. Even back here, even though we crossed it out and it didn't matter, I should make all of these capital M's because I'm looking at the larger of the two masses first. So this seems like there's information, but if I look at this, Chip, how many unknowns are there in this equation? How many unknowns?
2.
2. So can I solve it? Not yet. Very good. Right now I can't. M is known, but acceleration and tension are not known. And that's what we're trying to find, right? Acceleration and tension. So clearly we're going to need another equation. Does this help me right here? Unfortunately, it doesn't. Because Fn is only useful if we're using what? Come on, you can answer this question. Fn is only useful when referring to friction forces. Are we doing anything with friction right now? So Fn doesn't really help us to link stuff together unless there's friction involved. Keep track of that. Okay? Fn doesn't really help us too much. So,
You said big MA equals to small MA.
what we can do actually first, though, is look at the free body diagram and the equation for the second one, and we'll see if that results. But let's start with that before we do that. So looking at the second mass, for the second mass, so that was the first mass right there. Now for the second mass, I've got the sum of the forces in the y direction equals little m ay. So I've got tension acting up, the weight acting down, and that equals little m ay. The weight acting down is mg. I'm going to use little m because I'm on the smaller mass now. And there's my equation that I can use. So now I've got two equations right here. I've got those two equations right there. So unfortunately, it still looks like I have three unknowns until we recognize that first statement that I made to start today. So right now it looks like what's unknown? It looks like tension, AX, and AY. Again, I'm only using these two equations right here. Tension is unknown, AX is unknown, and AY is unknown. Everything else is known. M, G, those are all known values. So AX and AY are the problem right now, right? That's the issue. So how can we somehow make it work?
AX and AY have to be the same.
Give me more than that. You're right that they're the same magnitude, M. They're the same magnitude. You want to go a little bit further with your statement then? I'm telling you that the same value, this is pulling to the right, but this is pulling which way?
Down.
So this is going to be really negative A.
Negative, yeah.
You follow what I'm saying there? So the acceleration of this block moving to the right, the first one up here, is, we'll call this A. So if the value of this is, say, 3 meters per second squared, this value must be negative 3 meters per second squared because it's pulling down. It's accelerating downward. So what we do is, we instead of using AX and AY, we say what Emily said and call them both A, but for the one that's moving up and down, we call it negative A. Spence, sorry, go ahead.
I was just thinking, so the acceleration, the vertical acceleration for block S is 0, and the horizontal acceleration for block H is 0.
Correct. In block H, I didn't do the horizontal because there's no forces.
And then the magnitude of the
Accelerations are the same.
is equal.
But this is negative because it's going down. This is positive because it's going to the right. So now my governing equations are right here underlined in red. And now we can see that Ft and A are the only unknowns. Two equations, two unknowns, we're going to solve. Again, you can solve it in your calculator if you want with a system. You can plug in for big M and little m. But this is the kind of problem that's probably actually nice to solve algebraically so we can see the significance of our answer. So I'm going to slide this up a little bit. Okay, and what I'm going to do is I'm going to substitute for tension in the other one. So I'm going to take this expression right here and plug it in for tension right there. And the key is to recognize is that if you have one rope under tension, the tension it feels on both ends is the same. Ft in the first rope, Ft for this rope is the same throughout the entire rope. If I were to physically measure how much force is pulling the rope at any little fiber along the way, it will be the same the entire time. So I can replace that Ft with capital M, little a, and then the rest carry over. And then if I'm solving for acceleration, which I would be in this formula, I'm going to move things around a little bit. Looks like I'm writing mama. I know, right? And then I'm solving for little a, so I'm going to factor it out. Emphasize the capital and the lowercase m. We'll call them M1 and M2, either way. But make sure you emphasize it. And then as a result, our answer for A turns out to be mg over big M plus little m. Okay, that's a little m right there. I should maybe make that a little more clear. The numerator is a little m there. I make my little m's bubbly and the capital M's more rigid or angular. Okay? So that's the acceleration. And we can get a number because we have everything here. The number doesn't matter much though. You guys know that already, right? The number really doesn't mean much. And on your exam for multiple choice, I guarantee you the answer would be left like this. It would not be given as a number. Okay? It would not be given as a number, and M1 or big M and little m would not be given as values. Instead, you would solve this algebraically. But how does this help us? Let's think for a moment. Ready? Watch this. This is going to blow your mind. It really should. What if the first block, the one that's on the surface, the one that's sliding left to right, what if that block weren't there? What if the block sliding left to right just weren't there anymore? What would happen to this block? It would just, what acceleration would it fall with? Okay, take a look. Cancel out big M. You're left with little mg over little m. What happens to little m's? And what are you left with only? 9.8. The significance and the power to an algebraic solution is so obvious by looking at this. Literally, if the big block didn't exist, the answer would just become g. The m's would cancel there, and you would get just g. That's why we're solving algebraically, so we can understand the problem. Okay, so we can understand it. What if the little block didn't exist? Would the upper block move at all?
Nope.
Because nothing's pulling down on it, right? Okay, look. The little block doesn't exist. So what does little m become?
0.
So this whole thing is 0 over some number, which is 0. Very good. It's just 0. It's not your question. So the acceleration would equal 0, meaning this block would not slide to the right anymore if the little mass wasn't there to pull down on it. So the significance of the answer and the value makes so much sense when we look at the algebraic solution. Take a little rest of that. When we look at the algebraic solution, guys, the algebraic solution is so powerful. Now, if I want the tension force, here's what I'm going to do. I'm going to take this answer, I'm just going to plug it back in for acceleration up there. And let's do that. We get tension equals big M times the acceleration. And there's the tension force right there. Okay, there's the tension force right there. Am I going to discuss the tension force at all? Maybe for a moment. What can we do with this one? I mean, we could say the same concept, right? Everybody see the same concept? If the big mass didn't exist, take a look. The big mass didn't exist. 0 times anything is, so would there be any tension in the rope? No, because there's nothing pulling back. If the little mass didn't exist, this becomes 0, and then again 0 times anything is still 0. So the point is, if either of these masses weren't there, the rope would have no tension, which makes sense. If I just drop something with a rope off the end, the rope's just going to be doing this, right? That's all it's going to be doing, like a fishtail. It's not going to actually be pulling. It's not going to be taut. There's going to be no tension in the rope. So whether either of these if either of these masses were 0, tension automatically becomes 0, according to my algebraic solution. Okay? Again, the numerical part doesn't really matter. In case you're wondering, so you wanted to know maybe, the numbers would turn out to be 3.8 meters per second squared for acceleration and 13 newtons for tension. Okay, but again, you could go ahead and practice and go through this whole process if you don't believe that part. Let's go on to a second problem. Okay, this is going to be... Where are we? Oh, I know it first? Yeah, I do. Okay. This is going to be problem 5.04 on page 110. This is going to be 5.04 on page 110. Just give you guys the figures so you can see it.
Why does it specify that it's a box of sea biscuits?
This book has a tendency to do that. You notice that?
They have the weirdest examples.
What was that?
It was like a homeless man.
No.
It was like,
No, it's like
Wait, I have it. A hoodlum. It was a hoodlum throws a stone.
What does it say? A hoodlum?
A hoodlum
Throws
throws
a
a
brick
stone
through a window.
vertically downward.
You know, that's not very PC either, right? To use the phrase
Or-
hoodlum. It assumes that people from what is called like the hood would.
A bicycle, and then in parentheses, human-powered vehicle.
In case you know what it is, right? Okay.
Skunk foraging for trash food.
for trash.
What was that?
A skunk foraging for trash food.
Nice. For trash food. Alright. Alright, so in figure 5.15a, a cord pulls a box of sea biscuits up a long frictionless plane. Inclined at 30 degrees, the box has a mass of 5, the force from the cord has a magnitude of T equals 25 newtons, and it says what is the box's acceleration A along the plane. So this problem becomes tricky because it's on an inclined plane. And actually your book starts by saying this, and this is no joke, I'm reading this. Many students consider problems involving ramps, inclined planes, to be especially hard. This difficulty is probably the visual part because we work with a tilted coordinate, all this stuff. They're pretty much trying to set you up like saying you can't do it. Trust me, it's not hard. It is not hard. I'm going to go through something right now that will show you how to remember how to work these problems every single time. And you don't have to derive it any time. So let me go with starting first with a free body diagram. So I'm going to start with my object right here. I'm going to start by first putting tension coming from that cord. I'm then going to put a normal force like this. And then I'm going to put weight like this. And there's my free body diagram. The issue becomes the fact that nothing or not everything is perpendicular. That's why the book says it becomes a hard problem. So let's talk about this FG value here. The FG value is the one that I'd rather break up. Because if I think about this, well, FG is acting straight down, Mr. Howell, and the Y direction is down. But then FT and FN I have to break into components, right? I don't want to have to break up two forces into components. And clearly FT and FN are both angled. But I don't want to have to break them up into their X and Y values. So here's what I do. I start by tilting my axes. So let's go ahead and call this the Y direction. And let's go ahead and call this the X direction. And traditionally, down the ramp is considered the positive X direction. So not only are you tilting your axis, but you're kind of flipping your X-axis. So again, for the X direction, we're going to consider down the ramp to be positive in the X direction and up the ramp to be negative in the X direction. So because of that, what I need to do really is recognize that FG really pulls like this and like this. That's what FG is really doing. And notice what I did. I made a little rectangle. Turn your head, please. You'll see that this and this becomes this as hypotenuse. Think of like the X component, the Y component, the overall weight. So this is the X component, this is the Y component itself. Now, it turns out that the X component is always going to be FG sine theta, not cosine. That's where it gets tricky. And the Y component is always going to be FG cosine theta. So if you recall what I said, I don't know, a couple days ago, we can't have both the overall force and its components on the same diagram. Remember I said that? You can't draw both things on the same free body diagram or it's redundant. FG and those two blue components are the same thing. So I can only have one of them on my free body diagram. The one that's more important is the one in blue. So now what I'm going to do is just go like this. I'm going to say to myself, oh, that's gone. Okay, there's no longer weight pulling straight down. I broke it into its components. For the sake of time, I mean, it depends on last year, but you may have seen this last year, you may not have. For the sake of time, I'm not going to get into the derivation. It's on that same page that this problem is on. It shows you where cosine and sine come from. So this is all on page 110. So if you want to see that, you can look it up. But here's all you have to know. Inclined planes simply use this angle theta and switch sine and cosine. Normally, for the x component of something, you use the cosine. And for the y component, normally you use the sine. For inclined planes, simply switch them. It really doesn't matter the derivation about why that happens. It really doesn't right now. And for the sake of doing well in this test, I want you guys to just recognize that switch your cosine and sine for inclined planes. Now, that is not, by the way, take a look at my diagram real quick, look at the figure. If I had a force acting like this at a second angle, theta 2, that is not the same for that force. To break up this force, you've got Fy, which is F sine theta 2, and then Fx is F cosine theta 2. It's only for weight that we do this. Is that clear what I'm saying? It's only for weight that we do this. So it's not a generalized thing. I don't want you to be like, oh, no matter what angle it is on an inclined plane, I'm going to switch up cosine and sine. It's only for Fg, when we break it into components, that we switch cosine and sine. Now, with that said, this becomes an easy problem now. We simply look at the x and the y direction. Sum of the forces in the y direction tells me Fn, oops, let me put like a colon here, tells me Fn minus Fg cosine theta equals MAY. And that goes to 0. Again, why does AY go to 0 in this problem like the last one? Why did AY go to 0, Chip?
It's not coming off the
Plane.
ramp.
Ramp, very good. It is not levitating off the ramp. The rope is pulling it up the ramp, not off the ramp. The rope or the cord is pulling it up the ramp. Then we look at the x direction. And in the x direction we've got, remember, down the ramp is positive now for these problems. So we've got Fg sine theta acting positively because it's down the ramp. We've got the tension acting up the ramp, so that's negative. And that will equal MAX. Now, if the tension is equal to Fg sine theta, if these are equal, what do we know about the problem? These values are equal to each other. What would we know about this kind of a problem, Chip?
I was going to say, you said that side equals 0.
Which tells us what? This whole thing is 0. What must be 0 over here? S can't be 0.
Acceleration.
So when these are equal to each other, what state are we in?
Equilibrium.
No, we're in New York. Yes, we're in equilibrium. We're in a state of equilibrium. So in a state of equilibrium, we know that the acceleration is 0. So this will become 0 if these were balanced. But this problem says, determine the acceleration of the block. So there's a good chance it's not going to turn out to be 0, but let's figure it out. Let's go ahead and figure it out. So does the y direction help me at all? Do I need the y direction? Let's see, what do we know? In the problem, we're given tension is 25. Okay, that's good, I got that. We're given the mass is 5. Fg sine theta is really just 5 times gravity times the sine of the angle. So yeah, in this problem, I don't need the y direction at all. Everything I have is in the x direction. Fg is just mass times gravity. That's these two. Sine of theta is sine of 30 degrees. Minus the tension. Tension is given as 25 newtons. The mass is 5. Solve for AX. Solve for AX. And AX will turn out to be, what's the number? 0.1. Now, like last problem we had, it's really more important to get the algebraic solution. So let's do that. This becomes mg sine theta minus ft all over m equals ax. Okay, circled over there on the left is really the more important solution right there. And what does this tell me? Let's go through the process. This really does actually tell me a lot. Right, the number's great. Yeah, this is great. Okay, awesome, wonderful. And actually, this number would be negative, right? Should be negative because it's up the ramp. Or would it be down the ramp, actually? Let's see. Which one is greater? I'm using the book. I don't know if they consider up the ramp negative. Sine 30 is 1/2. 5 times 9.8 is around 50. So 49. It'll be negative 0.1 meters per second squared. Yeah. It'll be a negative here. Write down a negative here. I jotted down right there. Matt.
I also know why acceleration if it's going down.
Because remember, look at my axes. We tilted them, didn't we?
Uh-huh.
So look at the y-axis. The y-axis is this, right? See the y-axis right here?
Yeah.
So is the object literally accelerating this way ever?
No.
Is it accelerating this way ever?
No.
So AY is 0. Remember, it's the acceleration along what we are calling the y-axis, which in this diagram is tilted a little bit.
So, but that would also apply when it's on the ramp. Yep.
What do you mean?
So like it'd have an acceleration of 0.1 in just the picture of the box.
So this acceleration right here,
Yeah.
right here, means that it's going up the ramp like that. It's literally being pulled up the ramp.
Yeah.
Because down the ramp, we're considering the positive x direction.
Yeah.
And since we got a negative answer, it must be accelerating up the ramp. Not off of the ramp, up the ramp. Off of the ramp would give us AY. Off of the ramp would give us AY. Up the ramp is AX. Or down the ramp is AX. Okay? For inclined plane problems, there's almost never going to be a problem where it lifts off the ramp. It's always going to be acceleration along the ramp. Some textbooks will even call this the parallel acceleration, meaning parallel to the ramp, versus the perpendicular acceleration, meaning perpendicular from the ramp. I don't think there's a need to use parallel and perpendicular if we just call the axes x and y and tilde.
I just think because there's a change in y value, like what would that translate? Just like negligible.
What change in y value?
What is that's going up the ramps? Delta y is there's a delta y.
No, it's not. It's only delta x. Up the ramp is considered the x-axis. See, what you're missing is the tilted axis part.
I can't connect. I'm having a hard time like translating the tilted axis into like the real life scenario.
Well, here's what you do. You think about, okay, the x-axis is only this way, right? And our object either can go this way or this way. So we can only travel along the x-axis. Even though I get what you're saying, by seeing something move this way, you think, oh, it moves right and it moves up, right? So you think, oh, there's vertical acceleration. According to our diagram, we're considering the vertical this. And therefore, there's only horizontal acceleration. So if you want to call the ramp portion parallel and call this perpendicular, you can put a little perpendicular symbol and a parallel symbol if it helps. Some books have done that in the past. I don't do that traditionally, but you can if that helps you. And let's talk about the power of this answer though. Again, the acceleration is a function of a couple of things. The mass, the tension in the rope, and gravity, the rate at which it's going, and the angle too actually. What does the sine function do? As you go from 0 to 90, what does the sine function do? From 0 to 90. Think about it. What does the sine function do as theta changes from 0 to 90? Sine of 0 is 0. Sine of 30 is 0.5. Sine of 45 is 0.7071. Sine of 60 is 0.866. Sine of 90 is 1. What's happening to all of my values? They're getting bigger. So if I increase theta, this quantity is going to get larger and larger and larger. Which, if I think about it, if I keep increasing theta, I'm going to get a larger value over here in the answer. Well, that means that it might accelerate down the ramp. This number turned out to be less than this number when we plugged in. This was like 24 point something. This is 25. So this number is a little bit smaller than this one, which is why our answer was negative in the first place. But if I keep inclining this, eventually I'm going to get to an angle where the force pulling up is not enough to pull it up. And it's going to start to do what? It's going to start to slide back down. Because this value, remember, this value right here is this, the weight of the object pulling down the ramp. If the weight of the object pulling down the ramp exceeds the tension pulling up the ramp, it will slide down the ramp. In our problem, tension was greater than the weight pulling down. This number, let's actually get a number for this. Let's do 5 times 9.8 times 0.5. 5 times 9.8, 5 times 10 will be, so... 24 point something. 5? Okay, thank you. I'm like having brain fart math in my head here. So that's what we have. That's what the numerator is. This is 24.5 minus 25. So if I change theta now to be 60 degrees, this number gets a lot greater. 9.8 times 5 times the sine of 60 degrees. Man, what do you get for that? Seems like 30, 40?
42.
Yeah. So we get a number like 40 something minus 25, which means now the weight pulling down is more than tension pulling up. So if I keep making theta greater and greater and greater, eventually this number gets greater than this number, which yields a positive answer for acceleration, which means it slides down the positive x-axis down the ramp. So the values matter a lot. Again, if I change tension, the more I make tension, the faster it's going to accelerate up the ramp. You'd be like, if I'm just pulling it even harder, it's going to accelerate faster up the ramp because this number is getting greater and greater. And then the mass is hard to discuss because it's in both spots. We could technically cancel these out and put this ft over m, but that's not really worth it at this point. Okay? All right. There are a lot of problems in this section. Okay? There are a good amount of problems. I still want to do a couple more. I want to start one right now. I know we only have a couple minutes left, but I do want to start the next one. And it's an interesting question. It really is. So the first time I looked at it, this is that page. So the first time I looked at it, I was like, ooh, this is intriguing. And then I read through it a little bit, and I was like, okay, I could see why it's actually important. There's one. And then here's the diagram itself. So the problem is an example that's very intriguing. What it's giving us is it's giving us a graph of acceleration instead of the actual acceleration because the acceleration is no longer constant. Okay, the acceleration is variable in this problem. So that's what we're noticing here. The problem begins with a certain amount of acceleration and continues to decrease over time as theta changes. So it says an example where you must dig information out of a graph, not just read off a number. In 516a, two forces are applied. The one force, two forces are applied, our friction is 4, but only one force is indicated. That's F1 right here. It says that force has a fixed magnitude but can be applied at an adjustable angle. So this force, the angle can change depending on how you're pulling on it. F2 is a horizontal force and is fixed in both magnitude and angle, meaning it's not going to change. So F2 you could either draw this way or you can draw it this way. The angle is not changing there. And it's horizontal, so I know that it's got to have an angle of 0 degrees. Figure 516b gives us the horizontal acceleration of the block for any given value of theta when theta ranges from 0 to 90. And the question is, what is the value of acceleration of A for when theta equals 180 degrees? So there's a lot going on in this problem. So when we start this problem, it's really important to start by saying to ourselves, our free body diagram is this. F1 at an angle of theta, but F2 for now has to be horizontal. So I'm going to start by calling this F2. Yes, I know F2 could also be acting to the left. Horizontal means either all to the right or all to the left. It's one or the other. So I can draw my vector for F2 either all to the right or all to the left. I'm going to draw it to the right. And if my answer for F2 turns out to be negative, it means I drew it the wrong way. It means that the force should actually be flipped around on the other side. So for now, though, I'm going to draw it to the right. And what this does is this allows me to have one governing equation. Here it is. Ready? F1 cos theta plus F2 equals MAX. And this is from the sum of the forces in the x direction. The y direction doesn't give me anything at all in this problem. Okay, the y direction is not what I'm going to be focused on, just the x direction. So you guys have homework obviously due in 2 days. I'd love for you to practice the rest of this problem. And you can check your work because the answer is all worked out for you on page 111 to 112, I think. Yeah. I think it ends on it ends on 111 at the very bottom. So I'll give you a hint. This graph specifically points out two locations with an angle of 0 and an acceleration. With an angle of 90 and an acceleration. If you plug in an angle and an acceleration twice, you'll get how many equations? 2. And how many unknowns do you have? 2. So I recommend that you finish this off over the next 2 days in conjunction with homework from from 5.1 and 5.2. Okay, 5.1 and 5.2. 5.3 homework is going to be over the weekend. Okay, it's going to be over the weekend once we finish 5.3 on Friday. That's what 5.3 homework will be. So just keep this in the back of your mind. Okay, I have office hours right now, so you're welcome to hang out. If you have questions, just chill, relax. If you want to ask me any quick questions or anything lengthy, feel free to stay for a little while. I'll be here the whole time. Oh, the last thing I got to point out. Sorry, one more thing. I forgot to say it. We got to really push ourselves not to be doing like homework due on the day of in the recitation. And this is not Alex ratting anyone out at all. This is me being very, very like annoying to Alex, saying, "Hey, I really want to know like what is everybody doing every single day in recitation." So today he said that some people started the 5.152 homework as I suggested, but most were finishing up their lab that was due today. Try to get your work done before you come to school so that you can really utilize that recitation period to practice and go through problems. Again, this is not to everybody, but this was a general consensus. So I'm really pushing you guys. When you come to those recitation sessions, be ready to either start new problems or review work. But try not to think of that period as like, well, this is a period I can get work done that's due the same day. Does that make sense? Or else I'm going to have to stop making things due on day 5 and I'll have to make them due on day 4, which I don't really want to do. Okay? Does that make sense what I'm saying?
Thank you.
Have a good day, guys. Somebody's projectile launcher's out still. Anybody know who that is?
Let the mouse on the
Whose is it? Can you guys find cabbage and stuff?
Yeah, we had it in there, but we were using it yesterday to verify data, and I didn't have
No problem. When you get a chance, thank you. Oh, good. Cool. I just wanted to make sure I'm in line.
Yeah, we're fine.
Based on anything from the year that we've covered already. So we'll never get repeated. It'll always be something either that we covered the day before, the week before. Maybe there'll be a quiz on kinematics next week from last chapter or 2 chapters ago. So quizzes are just to keep you on your feet to get you tested and practice. Okay? Yep. Quiz.
It's big grandson, but sorry I can't cover the I'm still working, so.
I'm going to be here on Friday after school also. I was going to originally be here tomorrow, but there's no way I can stay tomorrow. But Friday I will also. Because I was out yesterday, so I thought I'll make it up for you guys. I'll send an email about that today. Okay?
I was really cold in my basketball outfit. I practiced after, so I was like, I'll put on sweatpants so I'm not like freezing.
And I think I like that, you know. Just, it's like shorts are this big and it's the winter time. That's
Yeah,
not
I'm like,
comfortable,
I'm
feeling
like,
awkward about it, right?
Yeah, as you're out, we're assuming no air resistance, right?
Unless stated ever, the assumption is always no air resistance. Yep. Regina, anything to go over, but not the quiz because George is taking it right now, but anything you want to review and go over?
Just the material on the quiz.
We said, hey, you know what? This graph here is telling me a lot of information. It's telling me that when the angle between the force and the horizontal is 0, meaning when it's like this, right here, but it's being pulled to the right, the acceleration is 3. So that is useful. That's really useful. What does that do? It gives me this equation. It tells me that I can write the following then. I could write F1 cosine of 0 plus F2 equals m times 3. That's what the first data point gives me. Now, this graph has how many data points though? How many data points does this graph have? Good, Max, well done. Not 2. The answer is not 2. You want to say 2, they tell you 2 of them. But it's infinitely many data points. I know that when the angle is 45 degrees, the acceleration is 2.5. Right there. When the angle is 22.5 degrees, it's like 2.75. So I can pick any data point to use. How many do I have to use though? How many do I have to use in this problem? I have to use how many?
2.
Why?
Because
You have like a system with 2 unknowns.
The mass was given in the problem. The mass was given as 4 kilograms. So this is known. So the unknowns are F1 and F2. So I cannot solve this equation right now. So if I look at the second part though, and I'll put a 4 in for mass now so we can see that that's not unknown. If I look at the second, so that was the first data point right here. Okay, now let's look at the second data point in blue. This data point tells me F1 cosine 90 plus F2 equals 4 times 0.5. What's the cosine of 90?
0.
Which one?
0.
0. Cosine of 0 is 1, right? So up here, this goes to 1, but this goes to 0. So the second equation in blue just gives me F2. There it is. So really, I didn't need to solve a system, technically. I could solve a 1-variable equation first, plug that in, which becomes a system in the end anyway. Okay, so it turns out that F2 in this problem is just 2 from that equation. Then if I take that value and plug it back in up there, we can get the value of F1. Again, because this is 0, it drops off. F2 is just 2. Plug the 2 in up here. This is going to be 12. 12 minus 2 will give me the F1 value. Okay? Will give me the F1 value. Now, are we done? Is that the whole problem? Does it say find F1 and F2? What does it say, Bridge? If? Yeah. So these are my numbers I've got right now, right? Those are the values I have for F1 and F2. But the question is not complete. The question says, if theta is 180, what happens? First of all, let's start by saying we could use the governing equation right here. Plug in F1, plug in cosine 180, plug in F2, plug in the mass, and solve for A. Everybody sees that? We know everything now. We can plug into here with 180 with the known values. That works. You can also use logic. Use logic. What is the cosine of 1, or what does 180 mean? What is 180? Yeah. It just means that F1 is acting that way. Well, that means that F1 is negative 10 because it's acting to the left. So if I draw my new free body diagram, when F1 is at an angle of 180, there's F1. And there's F2. So what's the net force? The net force is negative 8. And then we take that negative 8 and divide by the mass. Okay? Again, I can plug into the equation and get the answer with the work, or I could just say sum of the forces equals ma. The net force is negative 8. The mass is 4. Find the acceleration. The acceleration will be negative 2 meters per second squared. So sure, cosine 180 is negative 1. Negative 1 times 10 is negative 10. This becomes negative 10 plus 2. Well, I just got negative 8 by looking at the problem. So if you want to plug the 180 in, go ahead and do it. But recognize that 180, as Chip said, simply means we're acting to the left. Okay, that force is acting to the left. So a very good problem that you're going to see. Now, this would definitely not fall into a part 2 on a test. It's too easy for a part 2. This could absolutely be a multiple choice. The reasoning behind why it could be multiple choice is I can see this being 2 parts. They give the diagram and the scenario, and then they say, for questions 4 and 5, use the following, and then they'll ask 2 questions on this. One of them would have most likely been determine the forces, and the second would have been determine the acceleration if the force is at 180. Why would I see this as 2 multiple choice? Because 1 multiple choice would probably take you a little bit longer than it should. This is probably like, if I were to start this problem from scratch, it'd probably take me 5 minutes to really get to the solution for the whole problem. But for 2 multiple choice problems, then it's only like 2 minutes each in a sense. You see how I'm using my numbers of time on this test? Keep track of your time when you're taking my test, and then think of it on the AP exam. This is 2 separate problems, really, so I can see there's 2 multiple choice. But if you had to only do this, this would be a lengthy multiple choice problem. Okay, so I wouldn't see it asking you for all this information for 1 problem. I could see it being 2 problems back to back with the same setup. Okay, with the same setup. Any questions on this sample problem? Did people struggle on this at home? Was it easy? Was it difficult? What was your take on it in general? Remember I was saying I try to finish this up when you guys go home? Did you, be honest, give me a show of hands. Did you get it completely? Did you have no idea? Or were you like, either I didn't do it, or I'm not really sure, but I kind of had an idea? Where would you put yourself on the scale? And be honest with it. I really want to know. Okay, good. All right. And I'm trying to keep track so I know going forward the difficulty level of problems. This becomes difficult because it uses graphical parts with the diagram, which you usually don't see, right? Usually you don't see something where you're given like, ooh, this is acceleration as a function of theta. But on an AP exam, this is definitely a good problem because they like to use graphs on the AP exam. A lot of graphs are up here. Yeah?
When you deal with forces and you have to say F1 cosine theta, do you always do it in relativity to the positive?
Positive x direction. Yep. So if 180 is the number, Kara, it's going to be 180 from here, which is all the way around. If it were like, if they said the angle is negative 30, then it's that angle right there. Always with respect to the positive x-axis, unless stated otherwise. Then you have to actually adjust.
On one of the homework problems, the angle is measured to the y-axis, so would you switch cosine and sine?
Or you could just use the complementary of the angle. Yep, either one is fine.
Okay.
Inclined planes are always going to switch cosine and sine for the gravitational portion. The other ones are like the time we would. Yep. All right, let's continue. Let's keep moving on. Let's go to the elevator problem. The elevator problem is another classic AP example. So we're doing the elevator problem. This is on page 112. On page 112, the elevator problem. And again, this is I'm trying to get you guys a little bit of exposure to all the classic type of problems you could expect. Okay, the classic type of problems that you can expect on this. We're going to talk about tension problems. We're going to talk about friction problems. The next problem after this, we're going to talk about the two-block system problem. So these are all the types of problems you can expect to see. So although people would surely avoid getting to an elevator with you, suppose you weighed yourself on the elevator. In my class last year, I had my students do this as extra credit, if you recall. Get on an elevator, videotape the scale. You needed like an analog scale or something that doesn't like set in on a scale on a weight that can vary. And get the elevator, do it yourself when you go home. It's actually really, you know what it's going to be because the answer already. Because when you go down an elevator, what do you feel suddenly? You feel like you don't weigh as much. You feel a little lighter when the elevator accelerates downward. But when it accelerates upward, your legs feel heavier physically. So you kind of already know what the answer is. And use that knowledge to know whether it's going to be greater or less than your actual weight. So when I'm going down, I feel like I weigh less than I actually do. When I go up, or accelerate up, I should say, I feel like I weigh more. What about that interim period? So I'm on the 0th floor body. I hit the elevator. It starts to accelerate. Does it accelerate the whole way up? Sure does. If it did, yeah, exactly. You never stop. It can't accelerate the whole way up. You would never stop. Okay, unless it accelerated all the way up and then it decelerates dramatically at the end, which would be like, you would feel that really with a lot of your body. Yeah, you would literally feel a deceleration. If it did slow enough, your body would launch to the ceiling technically, yeah. Anyway, point being here, when you're in between floors, what are you doing? When you're in between floors, not at the beginning, not at the end, but in between.
Your velocity is constant.
So therefore, you're in a state of
Equilibrium.
So the weight you feel like when you're moving at a constant velocity is no different than your actual weight. Okay, your Fn, the normal force on your body, and you remember Fn is what you feel like, right? Fn is what you feel like because the floor responds. When you're moving at a constant velocity, Fn is equal to Fg. And we'll prove that in this example. But logically, you should already know this idea because of what you feel when you've done this yourself. So let's get into it. So it says here, first, would you weigh more or less or greater than? And we already discussed that idea. So a passenger of mass 72.2 kilograms stands on a platform scale in an elevator cab. So I'm going to draw an elevator real quick. Here's the scale, and here's the person. Beautiful, all right? I love it. Now, in this problem, what I'm going to be looking at is the person as the free body diagram. So here's the person right there. I know that the person has weight, so the person's weight acts down. I know that the scale pushes back up, and it pushes back up with whatever the normal force is. I don't know what the normal force is. I really don't. If the elevator were to just free fall, what would the normal force be? Zero. Think about it logically. If that elevator just dropped, you would also start dropping, but the scale would not feel you because you'd kind of be like a little gap between you and the scale most likely. Because the elevator would fall and then you would fall right behind it. So your feet would probably still be either on the scale or just off the scale, but the scale wouldn't feel any force acting down on you. That's what free fall is. It's literally what free fall is.
Isn't that how like zero gravity things work? Where like people get on and then the plane like cuts its engines?
Zero gravity, it accelerates downward with the exact acceleration. Take action.
Like the planes, they like you go on the plane and then like you kind of go upwards, and then they cut the engines and the plane just like falls.
The plane has to fall at exactly 9.8 meters per second because
Yeah, but there's no fuel, so it'll just fall out of the sky.
but air resistance is going to slow it down, and it's not going to slow you down.
They don't shut off the engines.
I think they actually accelerate downward slightly. I don't think they just shut off the engines. I think they have to actually put some slight thrust force downward. They did an OK Go video. There's a music video, right? Isn't that their music video? There is a band, yeah. Do you remember the video where they're like floating? There's a music video they put out a while ago.
I only know their treadmill one.
Ah, okay. Is that the one with the...
That's like the one that made them famous.
Like Usain
Where they're all like,
Bolt
they're on treadmills and they're like...
on
That was the Rube Goldberg one, right? It's a Rube Goldberg one.
Oh, that one was good.
That's really cool. Anyway, I'm not sure. Look that up. Is it a free fall? Because a free fall you would feel weightless for sure. If you were free falling, that's the concept you feel weightless. But I don't know if the plane itself free falls or if it nosedives at the exact acceleration.
Well, if it's a plane, it can't really free fall. Because the wings would cause lift so that it can't free fall by itself. So you have to accelerate down.
Unless the pitch was exactly negative 90 degrees, then there would
Yeah, but
the
then
lift
it
would
goes
only
straight down.
actually the air rushing over would cause it to move that way. Yeah. So it can't be free fall. It's got to be some acceleration downward to cause that feeling of weightlessness. Anyway, let's get back to that in a second. Let's talk about this first. So we want to know, first, the general solution for the scale reading, whatever the vertical motion is. Second, what if there were acceleration? Okay, or what if it were constant velocity? We'll see what that happens. So let's take a look at the free body diagram. We have it here. We know that the sum of the forces in the y direction equals ma. I don't write the x direction because there's nothing going on in the x direction. I know that Fn is pushing up, Fg is pulling down, and that equals may. And just as we suspected a moment ago, we said if, in the case where there's no acceleration in between floors, what happens? Fn equals Fg. For this to equal 0, these have to be the same value. So that's the first solution, or the first solution when you are at a constant velocity. So here's the generic value, and they want a scale reading, so let's make the scale reading equal. So may minus mg. So there's the answer for part A, the generic answer for a normal force. Remember, normal force measures, or a scale measures normal force. Write that down if you didn't know that. A scale measures normal force.
Couldn't you make that an equation where F net over G plus A equals M?
F net over G plus A.
Equals M.
Could you solve for M? Sure, you can solve for M.
So,
But is that what it says? I don't know.
well, no, wouldn't that be the general solution?
Part A says find a general solution for the scale reading, whatever the vertical motion. The scale reading is the normal force. So we want to solve for Fn.
Doesn't it show mass though?
No, the scale reading, remember, the scale reading is not a reading of your mass. It's a reading of your weight. But because the object is accelerating, your weight seems to look different. So it's Fn that you solve for when it says scale reading. Good question. Yeah. I can see why you see what Spence asked. He's like, don't you solve for m because the scale measures your mass. A scale doesn't really measure your mass unless you're using a triple beam balance that has a counter mass on the other side. Then you're physically measuring in grams, which is your mass. But a scale that we use measures your weight. But you guys know this. Oh, maybe you don't. Have you ever done it before? You step on the scale and you like push on something
Oh yeah.
or pull on something. When you push, you're applying force to the desk, which takes on some of your weight. So the scale reading will go down, because the scale is not reading your full weight anymore. But if I were to pull, now I'm causing the desk to be pulling down on my body, which causes the weight to go up. Try it when you go home. Bring a scale and bring it next to like a chair or a coffee table or something. Push down on the table, the scale reading will go down. Pull up on the table, the scale reading will go up. Because if you pull up on the table, it's like you're lifting it, right? If I were to literally just lift the calculator while on the scale, now the scale is going to read me plus the calculator. So if I lift on the table, I'm literally holding some of the weight of the table in my arm. And then the scale is holding me, which is holding part of the table. That's why the scale reading is going to go up if you pull up on the table. But if you push down on it, now it's only part of your weight that the scale is reading. So the scale is reading your apparent weight, really. Okay, what your weight feels like. Very similar, if you had it last year, with buoyancy, with fluid mechanics. We talked about buoyancy and the concept of it, and it's the net force that's acting on your body that you feel. That's the apparent weight between the buoyant force, the gravity, and the buoyant force balancing each other. Same idea, except normal force. Part B says, what does the scale read if the cab is stationary or if it's moving up at a constant 0.5 meters per second? So if it's a constant velocity, or if it's stationary, this whole thing becomes 0. Right? Literally, this thing becomes 0. I put minus. This should be a plus here. Please correct me, guys. Feel free to correct me. That should be a plus right there. So the MAY becomes 0. Okay, the MAY becomes 0 for part B, and it becomes FN equals 0 plus mg, which simply tells us that the scale reads your weight. When you're not moving, or when you're moving at a constant velocity, the scale, Fn, is equal to your actual weight. Your actual weight. The third scenario, I think there's a third part to it, right? Yeah. What does the scale read if your acceleration is upward at 3.2 or downward at 3.2? So let's look at part C now. So either your acceleration is 3.2 or negative 3.2. That's what part C is asking us. Well, this is going to prove exactly what we said a little while ago. When you accelerate upward, guys, focus. When you accelerate upward, you feel like you weigh more than you actually do. So look at the equation, people. If you accelerate upward, A is positive, right? If A is positive, that goes in right here. This makes this number more positive. Plus another positive number makes the Fn even greater. So I don't even have to plug in the 3.2 to see that. Because if this number is positive, it's just going to increase this value. But if this number is negative, and I plug it in, it's going to decrease that value, which makes you feel like you weigh less. Let's see that happening. Fn equals, what is the mass given as? 72.2. 72.2 times 3.2 plus 72.2 times 9.8. That's what the scale reads when you're accelerating upward. And then when you accelerate downward, you have the exact same thing, but this is a negative 3.2 now. And then the right side is the same. Okay, nothing changes except the acceleration sign is what changes here. These are 72.2s. All right, so numbers-wise, just so you can physically see what you actually get here, you're going to get 939 for the first one, and you're going to get 477 for the second one. Well, what's the actual weight of this person here? What's the actual weight of the person? What does it come out to be?
Well, I don't know. It's going to be around 700 though.
Because it's, how did you come up with that? Yeah. In between the values.
It's 707.56.
Thank you. Okay, and that makes sense. You actually weigh 707 newtons. When you're accelerating upward at that rate of 3.2 meters per second, that's what you feel like you weigh. You weigh more. You feel like you weigh more. But when you're going downward, you feel like you weigh less. You feel like you weigh less on the way down. Okay? Elevator problem, classic problem on an AP exam. Especially multiple choice. Especially multiple choice. Okay, definitely too easy for a part 2. definitely too easy for part 2. It would be combined with a lot of other stuff if you had an elevator problem. You had probably something rotating within it. You might have something falling from the top of the elevator with gravitational as the elevator moves up. It would have to be far more complex than this for part 2. Okay? Next class. This is from the next page on page 113. This is the 2-block system. Okay, the 2-block system. Let's take a look at it. So we see, let me see, here we go. Oops. There it is. All right. Some homework problems involve objects that move together. This is really important, especially because we have 2-body systems or where there's a rope connecting the two. Remember last class we looked at that example with the rope over the pulley? Well, that rope caused us to recognize that the accelerated motion of the block hanging will be equal to the accelerated motion of the block on the actual surface. The same thing happens here. We've got this problem now. I don't know if the diagram's up here yet, but we have 2 blocks that are next to each other. Okay, they're literally adjacent to one another. So we've got this larger and smaller block here. The diagram that I didn't include looks like this. Okay, and there's an applied force on the objects. This is the diagram that was given in there. Now, the problem says, what is the acceleration of the blocks? What is the acceleration? And in this problem, the bigger block is the bigger mass. You're going to see that on the exam as well. The same thing occurs. Okay, you'll see that the block that's larger will have the larger mass. It's not obviously true because you guys know that size does not indicate mass if your density is different. And this is 6 kilograms. Okay, but that's what's given in the problem. A and B are 1 and 2, whatever. It doesn't matter, right? Let me go A and B to be consistent. A, and that's B.
So is block B creating force on the block?
Well, that's what we're going to talk about. Exactly. That's exactly it. This is Newton's third law that we're going to look at. You guys need to stop it. Everyone needs to focus. You're like intently watching something. I know. I'm not like stupid. Come on. All right. So there's a force being applied to the smaller block. The block is 4 kilograms. That block is then pushing the larger block. So as Tristan already recognized, if I'm pushing a larger block with a smaller block, so this is the scenario right here. Okay? Larger block, smaller block is the marker. I'm applying a force. That force is then transmitted to the larger block. And how are they moving? They're moving as a unit. Very good. As a system. Very good. So the idea here is that the acceleration of each block is the same. And that's key to this entire problem. So what we can do is we can draw the free body diagram of each block. And then the free body diagram of the system. Both. Let's use the word system for now on. System. So block A, we've got applied force to the right. We've got the reaction force, a force on block A from block B. My subscripts are going to be really important here. So this is block A, free body diagram. There's an applied force acting to the right. As Tristan said, block B is going to push back on block A. Write this down if you're not familiar with this from last year. This means a force on A from B. It's always written in that order. It's going to be written that way on AP exam if you see it that way. On A from B. It's just the traditional nomenclature, so don't switch it up just to switch it up. You can do that, but then recognize that you're always going to have to switch it up on the exam, so it wouldn't make sense to do that.
It's kind of like the normal force from B when you're like pushing on it.
Yeah, so it's I call it reaction forces.
Okay.
It's a reaction to the force it's feeling. But yes, it's equivalent, or it's analogous to a normal force. Because a normal force reacts to the weight.
Right.
Same concept. Object B. This is the key part here. This is the key part. What force acts, or forces, or force, either one, acts directly on object B?
The force on B from A.
Good. The force on B from A. So let's do this and write on B from A. The force F in the diagram does not act on block B. Indirectly it does, but directly it doesn't. Do you see the difference here? A free body diagram is a diagram of all forces acting directly on the object. Block A is what pushes block B. The force pushes block A. But the force does not, it's like in Star Wars, the force does not push block B. It does not push block B. It's the force from block A that acts on block B. You have a question?
I have two questions. So, F right there, that's F applied, right?
Yep, F applied. Did they call that F applied? Yeah.
Yeah.
Go ahead, keep going.
And
Second question?
F of B on A, is that the same as F applied?
This is the force here.
Or FBA.
This is the force acting on block B from block A.
Yeah, but would it be the same as?
Think about it. We're going to get to the answer. We'll come up with an answer in a moment. Start thinking about it as you go through. They're called internal forces within these. Internal forces because they're between the blocks. Now, the entire system, if we put them together, has its own free body diagram. And it's simply this. Okay? So those are my three free body diagrams for this problem. It is extremely, extremely useful to draw a free body diagram for each individual object. But you're going to notice in this course, so many times will we draw a free body diagram for the entire system. Okay, that's the extra FBD that you probably didn't see much of last year. The entire system's free body diagram. So this is what we have going on in this problem right now, right? We've got these three scenarios. So let's look at what we can do. Anything in the y direction? No. So we're not going to do sum of the force in the y direction. So I don't even need to write Fx. I could just write F equals ma for this problem. Because it's only horizontal motion that I'm worried about. So if I look at these three, I could start by saying to myself, all right, let's look at the first block. All right, so block A's equation. We've got F applied minus FAB equals the mass of block A times the acceleration of block A. This is the equation from block A's free body diagram. Then we've got block B. Block B. We know FBA pushes right, and that equals the mass of block B times its acceleration. There's the second equation. And last but not least, the third equation. We know that the applied force acts on the system. And what do I write for mass? What do I write for mass? For the system. The system.
MA plus B, MB.
Very good. Times what though now? Just A. And what else do we have to denote and recognize? That A is same as all of these. Sure, we use subscripts when we write them for those specific items. But recognition of the fact that A for the system equals A sub A, which equals A sub B, they're all the same. So call them all A at this point. Okay, if you need to write that up here, you can write it at the top. AA equals AB, which equals what we're going to call A. So let's get rid of the subscripts for the first two equations there. They're not necessary. And now what we notice is this. How many unknowns do we have, people? How many unknowns? Spence? 3. 4. I think 3. Because masses are given, I think, no problem.
Mass and force.
Huh? So we actually only have how many unknowns then? Only have 2 that we have. FBA, which is one force, these are the same forces equal and opposite each other. And then acceleration is the unknown.
Can you define FBA?
Let's figure out what it is. The problem doesn't ask us for it, but we're going to inherently find it anyway. But yeah, good recognition here. F applied is given, and the masses are all given. FAB and FBA, although looking like different variables, we should know Newton's third law. If block A pushes block B is going to push back, right? So we know that those values are going to be equivalent. But let's prove that that's true. Make believe we thought those three things were different. Make believe FBA and FAB are different. That becomes 2 variables. The third variable is acceleration. 3 equations, 3 unknowns if we want to think of it that way. We could still solve for FAB and FBA separately from each other.
So FAB and FBA are like the same. If you say there's not
Because they're internal forces. Internal forces have to equal 0. They're going to always cancel each other out. That's like a rope pulling on an object from one object to the other. The tension here equates to the tension here. They balance each other. That's FBA and FAB. But let's prove it mathematically so you can see it better. So let's go ahead and take a look at this. The first, well, let's see, which equation could we actually use? The third one we could solve, right? It looks like the third one we could solve already for acceleration. Yeah, we have all the information. What's the applied force in this problem? So this third equation becomes, this becomes 20 equals 4 plus 6 times A. Okay, so yes, A is going to yield 2 meters per second. Right? So that's the acceleration of the problem, and that comes from only the third equation there. So without the system equation, could we have gotten A? Could not. Could not. Okay, and that's a problem here. I think, could we have done it this way actually? We probably could have done a system with these two.
You could plug in 6A for.
You could have done it here, but then you have to make the assumption that you know that these are equal and opposite each other. So if you didn't have the third equation, you could still solve, but you have to know the concept that these are equivalent. Because this is known, this is known, this is known. This is 1 unknown, 2 unknowns, 3 unknowns. So at first it looks like 3 unknowns here with only 2 equations. But if you recognize that these are the same, then it becomes 1 unknown, and then that's the second unknown. So you could solve it if you knew that concept. But let's make believe we didn't know that because that's what we're proving here. So now we know acceleration is 2. Let's solve this equation. FBA equals mass of block B times 2, which equals 12. That's FBA. Again, the acceleration we got from the system is the same acceleration that we will use for each independent block. So this becomes just 6 times 2. 2 is our answer from the previous part. I'm not putting units, guys. Sorry, I'm just being lazy at times. So please, on tests, obviously, remember to put units on stuff. Max. Oh, I had a hand. Sorry. How about this last part here? Let's take a look at this equation, and let's solve for FAB. Let's solve this last equation for FAB. So given the values that we know now, let's see, F applied is 20 minus FAB equals 4 times 2. Negative FAB equals negative 12. Therefore, FAB equals 12. Okay, yielding the same answer that we got earlier. Again, I'm taking now the first equation. I'm plugging in what we know, the applied force. We know the mass of block A. We know the acceleration of the system was 2. So this becomes just 8 minus 20, yielding negative 12, making it positive 12. So FAB and FBA are indeed the same values. Chip?
So is block A and block B are experiencing the same force, right?
Net force.
It's just the same net force, but the force being applied on A from B is equal to the force being applied on B from A.
Correct.
Right? So
Correct.
like, they have the same internal force,
Correct.
but then also the external force.
The external force is technically applying itself only to block A, right? Not to block B, really.
Right.
But block B does feel it intrinsically because it's a system there. And that's where the internal force transmits it. That's why FBA and FAB are in the problem. Because that FAB and FBA is physically the way for the first block to push the second block along. And we're going to do the same thing with ropes, okay, with cords, with tension. Okay, so where are we at right now? Let me just take a look. Yeah, go for it. That was the last problem in this section. So I want to do another one, though, with tension involved. So I'm going to look at your sample problems here next. Give me a minute. Let me figure out which one I want to actually use. You guys have homework in this over the weekend. Keep that in mind. Okay, you have homework in this section over the weekend. Some of the homework problems give you like velocity functions. They'll give you a velocity function in the homework problem, and then have you do work on the problem, and we need the acceleration. So what do you have to remember when you need the acceleration? Take the derivative and plug in the time.
There was one like that.
Okay. On the 5152 homework? Good. So you are used to that. So 2 derivatives to get the acceleration function? Good. I'm trying to include that so you guys recognize how that's going to show up on the exam also. Actually, let's do another inclined plane problem. I think those are tougher than the other ones, actually. Does that work? Inclined plane? We'll do another example of that? So let's look. I probably gave this to you for homework. I can't recall if I did or did not, though. But for now, I'm going to do it anyway. All right, so let's look at number 34 on page 119. Is it in your problem set, though? So it's all right. We'll do it anyway. I'm just trying to find a problem that's new or that's unique.
What is the problem set?
Before the test. I don't know if I put a due date up yet, actually. Your test, if I recall, is not until... Yeah, so not next week, but the following week on Monday, I think, right? On Monday. The juniors are on junior retreat. So theirs is earlier, yours is a little bit later. I was tempted to put it on that Wednesday, but people miss school a lot for Thanksgiving. And the day is always shorter because there's Mass. So that's why it's on that Monday. Keep that in mind. This is on page 119. Yep. Topics-wise, it will definitely be 5.1, 5.2, 5.3. And what I'd like to do next 2 classes is a lab, and then, is 6.1 and then a lab. So it'll probably also cover 6.1. Okay, but that is not on the problem set yet. I have to put that up. Chapter 5 is all there, but not
What
that.
is 6-1?
It'll most likely cover, 6.1 is friction.
Oh.
Yeah. 6.1 starts friction. 6.2 talks about air resistance, where we get to differential equations and integration. That's why I've been kind of holding off on that, because you're doing that now in calc, antiderivatives. And then 6.3, forget. Oh, look, I forget. But 6.1 is friction. 6.2 is specific types of friction, air resistance. I forget what 6.3 is bothering me now. 6.3 is... Did they not say in the beginning of the chapter? No. Friction, air resistance, terminal velocity. Circular motion. 6.3 is circular motion. Okay, so we're going to get to that at some point. So when we talk about spinning an object and the force actually affected it. Yeah.
This is just a question for like what we're learning.
Yeah.
Are we ever going to do harmonics?
Yeah, so simple harmonic motion is going to be probably one of the very last topics of the year. That'll be probably the very last topic or one of the last topics of the year. After this, we're going to get into momentum conservation and energy. Then we're going to get into rotational stuff. Then we're going to get into vibrations and simple harmonic motion. And we'll talk about gravity and universal gravitational pull of planets, but that'll play a role later on. All right. So in this problem, a crate, listen please, a crate is pushed at a constant speed up a frictionless ramp. The ramp's angle is 30 degrees. The force is horizontal. So be careful, because I've been calling horizontal up and down the plane. Remember last class we talked about this tilting of the axis? So they're calling it horizontal. So it's not actually horizontal compared to what I'm going to draw in a moment. So keep that in mind. But it's on the diagram at least. It says, what is the magnitude of F and what is the force on the crate from the ramp? So what is part B asking us to find? The normal force. Fn, the normal force. So let's start with the free body diagram over here. We've got the weight pulling down. We've got the normal force acting away from the ramp. And we've got the applied force into the ramp. So this may be a problem where you'd say, you know what? Let's just break up the normal force of the components instead. And leave the xy axis the normal way. Because this is acting along the normal y-axis we would use. This is acting along the normal x-axis. So we could just break this into components and do the problem. And that is absolutely fine. You can do that. I personally, when I took this as a student, never did that. Because it caused some confusion, and then I had to actually rederive stuff. So I personally like to break up gravity every time. And I break up gravity into the portion that's down the ramp and the portion that's into the ramp. Okay, so if you need to draw the ramp, go ahead and draw the ramp in the diagram as well. Here's the ramp itself. Come on, that's terrible. Here's the ramp itself, okay? And it's not a perfect 30-degree angle, I apologize. So when I'm drawing this, I'm going to start, if I take the approach that I was talking about, by calling these my axes. I'm going to call this X, and I'm going to call this Y. So what we'll recognize is that the components of the force applied have to actually be determined as well. the components of the force applied have to be determined as well. But that's actually not too bad, and we'll discuss that in a moment. So if I were to redraw this diagram now with components for gravity, so this is Fg here, this is Fn right here, and that's the applied force right there. And I should not have labeled the y-axis twice, sorry. If I were to draw my Fg in its component form, it would look like this. And from last class, if you recall, I told you, you want to see the derivation, take a look. I'm trying to pass through this class a little faster than we are going right now. So remember, please, that cosine and sine are switched for inclined plane gravitational portions. The x is sine now and the y is cosine. And the x is sine and the y is cosine. But the question comes about from the force applied F. So I'm going to first draw the normal force. Let's get that in there. There's the normal force. Again, this is our y-axis here, and this is our x-axis right here. You can see those in blue now. But now that force that was applied, that's going to be a little bit tricky because we have to break it up, right? So what I would recommend you do is this. I would recommend that you start labeling the original diagram with angles. So take a look at the original diagram. Here's the ramp. Label this theta right here. So go back up to the original, please. Take a look at what I'm labeling. Take a look. This is the same angle as this. This is parallel lines cut by a transversal. These are corresponding angles. These are both considered to be theta. So this is theta right here, which makes this angle 90 minus theta. You see how I'm labeling my diagram right up here. This is why trig was so important when you took geometry and pre-calc. Theta is given here, which means it must be there, which makes that 90 minus theta. Now, I want to break up that F value into its x and y components. And what I'll recognize here is that if I do this, do it with me please, take your head again and do this, tilt your head like that. You're going to notice that if I were to look at this diagram, this is acting to the right and then down. This force is acting to the right and then down. If I were to tilt my head like that. And I can see it by making my triangle right here. Making my triangle. So when I look at this kind of a problem, I want to visualize, I'll use green, I want to visualize this force as like there's Fx right there, and there's an Fy value right there. Okay, take a look at that green triangle right there I'm talking about. So if I want to know how much of it is pushing in the x direction, and I've got my angle theta, remember that I can use the cosine of the angle itself to get the x component. I'm not switching them. I'm not on gravity right now. So this is really F cosine theta right there. And this is F sine theta right there. So those labels are what I'm going to now put on this diagram over here. So I'm going to use another, I'll use black again actually here. And I'll say this is FPX. Or Fx. There's no P there. I thought we put P for push. Just Fx, meaning the force applied in the x direction. And that's going to equal F times the cosine of theta. And then we have an additional force acting in the y direction. And take a look at how I'm going to draw it. Another arrow I'm going to draw here. See? I'm not drawing this arrow much longer on purpose. I'm only doing it to get past the text here. I can put this arrow slightly larger, showing that it's acting down into the ramp as well. F sine theta.
You're only switching the sine and cosine for gravity.
Correct. Correct. Only for gravity, yep. Okay. So that's my problem right here. That's my problem. I can, in 30 seconds, I could show you real quick why I'm switching the angle for gravity. I'm going to show you real quick. It's really simple, actually. Now that we have our diagram drawn. Watch where I'm going to point to, okay? This is theta, right? Everybody see this? Take a look, take a look. This is theta, what I'm pointing to. So what is this angle right here? 90 minus theta, which makes this angle right here just theta. So theta is given between the force of gravity and the what axis, though? And what do we always say we want to use? The force and so we really want this angle, don't we? This is the angle we'd be using to break up gravity into components. But this angle is not theta. This is 90 minus theta. So for gravity, either I could use mg and then cosine of 90 minus theta, or I could just do sine of theta. Because remember, your cofunctions are equal. The sine of 10 equals the cosine of 80. So what I'm showing you here is that if I were to use this angle, which is the proper angle, it would be 90 minus theta. That would be a cosine again, 90 minus theta. That would be a sine again, 90 minus theta. So if you like the idea of keeping sine and cosine the way they are always, just remember for gravity, use 90 minus theta. So either you can make this 90 minus theta and keep it as cosine, or make this sine and keep it as theta. It's the same thing in the end. Okay, but that's the rationale as to why you're switching them. But you can see it more in your textbook. They do a whole derivation with all the triangles, but that's what I'm literally showing you up here with these triangles. Now, with all this said, we've got our forces. The free body diagram is the most important part. After that, this is easy. If you can't do algebra, you're in the wrong class. I'm not saying that seriously. You're all fine. You're all doing great algebra. But seriously, right? If you couldn't solve it from here out, you don't belong in the class because now it's just easy stuff. The part we just did was the hard part. Now it's just, okay, sum together the forces in the x equals ma. Sum together the force in the y equals ma. It's always equal to ma. That's why the topic of forces is actually not that bad. It's the one governing equation you will always use. When we get to friction, you'll have to replace FF with mu Fn, and that becomes a little trickier, but really not much. Okay, so let's look at the sum of the forces in the x direction. What's the acceleration in this problem? What's the acceleration given as?
0.
Why?
Because it's at constant speed.
Good. Constant speed, it says, right? Constant speed in the problem. So acceleration is 0. So we've got in the x direction, we've got pulling down the ramp, which we're considering positive down the ramp. We've got, let me write it out actually, mg sine theta minus f cos theta equal to 0. Again, I'll point to it so you can see it better. Down the ramp is mg sine theta. We're calling that the positive x direction. Up the ramp is f cosine theta. We're calling that the negative x direction, so that gets a negative sign. It doesn't matter if you call up the ramp positive, that's fine. If you call up the ramp positive, what happens to these two? What happens to these two if you call up the ramp positive? They just switch. They just switch each other. That's it. So that's my x equation. Can I solve this equation? Let's see. I've got theta. Good. I've got mass. Good. I've got gravity. So yeah, at this point, I could determine the value of f. I could determine the value of f. So let's go ahead and do that. F is going to equal mg sine theta over cosine theta. Oh, look at that. So f is really just what? Mg tan theta. Right? Mg tan theta. Listen, the AP exam likes to mess with your head. Here's what they're going to do. Ready? They're going to do it. And you're going to be pissed. You're going to be really pissed. It's going to say the following in the problem. Theta is not given. Theta is not given. Instead, what will they do? They'll literally say, the value of tangent theta equals 0.8. They'll tell you tangent theta. And you're like, where am I going to use tangent theta in this problem? I should have been given theta. I can't do this problem without theta. But it turns out that you don't need theta. All you need is the tangent of theta to get f. You see what I'm saying here? So I don't have to tell you that theta is 30 degrees. I could on the test and on the AP exam, they will do this. They'll give you a ratio, like they'll say sine of theta equals 0.427. By all means, you could go second sine 0.427, get the angle, and you could use that angle in the entire problem. You could do that for sure. But I'm telling you now, they'll probably make it trickier so it's tougher. They might say the value of tangent theta is called alpha. They're defining alpha as the tangent of theta. Determine the force as a function of alpha. Well, you would just replace this with alpha. mg alpha, that's the force applied. You follow what I'm getting at here? The exam does not always give you numbers. So we have to recognize that things like sine over cosine equals tangent is really important. So if you're doing the problem, you're like, I can't solve this because I'm not given enough. There's a good chance, one of two things. Something cancels out, and remember how m drops off a lot for mass, Or there's a simplification somewhere that makes the problem now doable, solvable, whatever you want to call it. Part B, that was part A right there. We get a number for that, whatever that number is. Part B, find the force on the crate from the ramp. Find the force on the crate from the ramp. What did we say that was again? What's the word for that? Normal force. So we're looking for normal force. Normal force is in the y direction. So sum of the forces in the y direction equals 0. Why am I putting 0 right away? What are we really pretty much assuming for these problems? It's going to almost always happen, Matt.
There's no vertical acceleration.
Because it's not doing what?
Go up or down.
It's not lifting off the ramp.
Oh, yeah.
Not, it's going up the ramp and down the ramp, but it's not lifting off of the ramp ever. Unless it's told it's lifting off the ramp, then you have acceleration. So that equals 0. We've got Fn upward. We've got mg cosine theta downward. And we've got f sine theta downward. And that equals 0. Again, take a look at the problem. Everything is known except for f. But we solved for f in part A. So let's go ahead and get a solution for Fn. Now where I have f, I'm going to replace it. And that's what your answer for Fn is. All I'm doing for Fn is moving these two expressions over to the right side. And then where I had f, I took in my answer from the last part and plugged it in. So I take this equivalent expression and plug that in for f right there. Okay, but say?
Let's do mg tan theta over 2. Because it's sine 30.
Oh, because the angle is 30? Sorry. Yeah, if the angle is 30, then yeah, by all means. Sure. But we're not plugging in numbers right now, so I wouldn't do that in this problem. This is a generic. I thought you were trying to simplify. This would become mg sine squared over cosine. You could do that, because this is sine over cosine, sine times sine is sine squared. And then sine squared, maybe do 1 minus cosine squared with one of your Pythagorean triples. That could come and play a role. Yeah, actually, that would really be useful for this. You see what I'm doing right now? If the problem did not define tangent theta, if the problem defined tangent theta as alpha, and then later on it said the cosine of theta is beta, here it would seem like I couldn't answer because I have tan and sine, right? But really, if I wanted to, this is just getting into your trig a little bit more, I could rewrite this as Fn equals mg cosine theta plus mg sine squared theta over cosine theta. And then sine squared theta is really 1 minus cosine squared theta. Come on. Mg 1 minus cosine squared theta all over cosine theta. And then this thing carries down. Why am I pointing this out right now? Why am I pointing this out, this last step? Multiple choice problems. Maybe they define tangent of theta as alpha, and they define cosine of theta as beta. This becomes beta, this becomes beta. This is 1 minus beta squared. Follow what I'm saying right now? So the angle does not need to be given, yet the expressions can be defined. Okay? Good job with this, guys. Again, this is 5-3. I know it's a heavy material. In the next class, we're going to get into friction. We're going to do a lab to determine how we can calculate the coefficient of friction for static scenarios. For kinetic, we'll talk about it and do another one of those procedural types to see how you would do it, but it's much easier to do it that way. And we did it last year, some of you that had it last year.